So in our last class, we got an introduction to exponential functions. These were the functions that had equations that looked like f of x equals a times b to the x, where the role of a here is played by the vertical intercept, the y-intercept, if you like, which has the same meaning that y-intercepts always do. It's the value of this function, the value of y when x is equal to 0. And then b, which is called the base, probably the most important quantity in an exponential function. This is an answer to the question, when we add 1 to x, we multiply the value of y by b, right? So that's the meaning of base. And this is what it was to be an exponential function in our last class, was to relate addition in my independent variable with a consistent multiplication in my dependent variable. So when I add 1 to x, I always multiply the value of y by b, where b is by definition the base of my exponential function. So what we want to be able to do today is to increase the variety of kinds of phenomena that we can model with exponential functions by applying what we know about graph transformations. So graph transformations we're talking about here are horizontal and vertical reflections, horizontal and vertical stretches, and horizontal and vertical shifts. All right, the 6 different kinds of graph transformations we talked about at the end of the last chapter. If we apply those to exponential functions, what kinds of new phenomena can we model? And then what does that do to things like the domain and the range and the end behavior asymptotes of my exponential function? So that'll be the first topic for today. In the second topic, we'll get an introduction to the natural number e, and we'll do a little bit of work with solving exponential equations and when can they be solved today using technology. What you're asked to do is answer some questions about the properties of each of these functions. Is it always increasing or always decreasing? Concave up or concave down? We talked about that in our last class. What is its end behavior? Does it increase without bound? Does it crash through the ceiling? Does it decrease without bound? Does it crash through the floor as we go all the way up to the right end of the graph? Or does it increase or decrease toward a finite value? So let's just look at one quick example of what answers to those questions tend to look like. If I just take, let's say I take f of t equals negative 12 times 1.2. Now let me use 1.5 to the power t. Something. So there's an example of an exponential function. How would I answer these questions for that function? First of all, what is the y-intercept for this exponential function? 0, comma, negative 12. Right, this negative 12 that's out in the front, the coefficient of my exponential piece, that tells me my y-intercept, negative 12. 0, negative 12. So I don't usually like using this language, but I'll use it in this case. We can kind of think of this as our starting point for my exponential function. And then what happens to this value, negative 12, as we move to the right? What is this 1.5 telling me?
It's going to be increasing.
It's going to be increasing how? So, say that again. So let me ask it this way. What is the percentage increase over every 1 unit of change in the t variable? 50%. 1.5 is the thing we're multiplying by, and when I multiply something by 1.5, I increase it by 50%. Right. So whichever way you like to see that. So if I go to the right by 1 unit on this graph, from 0 to 1, for example, then I'm going to be multiplying negative 12 by 1.5. That gives me negative 18. Right? That's a 50% increase. But even though we call it an increase, which direction do we actually go on this graph? Yeah, we actually end up going down, right? We end up subtracting 6 because we're multiplying a negative number by 1.5, right? And so the next point on my graph that I might write here is 1 comma negative 18. What's going to happen from that point if I go forward 1 more? I'm going to times that by 1.5, and I'm going to end up going even further down. So when I draw my graph out, at least on this side of the axis, it looks like, well, how would I answer? Well, let's do parts 1 and 2 first. Is this graph, do you think, going to be always increasing or always decreasing? Always decreasing. As we go from left to right, this graph is going downward. Okay. That's true for the piece of the graph that I sketched here. It would also be true if I continued to the left. Let's think about that for a second. If I subtract 1 instead of add 1, what do you think I'm going to do to the y value? If when I add 1, I multiply by 1.5, what happens when I subtract 1? What's the opposite of dividing by 1.5? Oh, I just gave it away.
Yeah,
Dividing by 1.5. Yeah, that's where my brain is this afternoon. I ruined the element of surprise. Divide by 1.5. Divide by 1.5. And so that's the same thing as dividing by 3/2, which is the same as multiplying by 2/3. And so if I multiply negative 12 by 2/3, I get negative 8. I hope I have that right. And so we end up looking like that. And as I continue going to the left, I'm going to keep dividing by 1.5. What happens if I continually divide a number by 1.5? What's the end of that story? So the t value goes all the way down to negative infinity, but what is the y value doing?
It'll approach 0, but it won't actually ever.
It will approach 0, but it never will actually get there. If I had a 4-function calculator, I could do this. Maybe I can just do this on the screen real quickly, right? So I had negative 12, and I divided it by 1.5. And that gave me negative 8. Right? And then if I divide that by 1.5, I get negative 5.3. If I divide that by 1.5, and again, and again, again, and again, and again, and again, and again, and again, this is the kind of thing that calculators are great at, right? This number keeps getting smaller and smaller, closer and closer to 0. It's actually getting greater and greater, right, because it's negative. But it's getting closer and closer to 0, but it never quite arrives at 0. So what does that tell us about this graph? Let me go back to the graph that we had on the screen here. Not this screen. The other screen. What's going to happen to my graph as I go all the way out to the left?
It'll approach 0.
It approaches 0. The 0 here meaning the x-axis, horizontal axis. I guess it's the t-axis in this example, right? But it never quite ever gets there. What did we call that last time? An asymptote, a horizontal asymptote. Horizontal asymptote at t equals 0. Asymptote at y equals 0. Right. Okay, so we decided that this function is always decreasing. Is it always concave up or always concave down?
Always concave down.
It looks like it's always concave down. If it were to rain on top of this curve, the rain would scatter, would run off, as opposed to collecting, right? Another way to say it is if I'm riding on an airplane going this way, I'm feeling the negative g-forces pushing me up into the ceiling instead of positive g-forces pushing me into my seat. Right? So this is a concave down and decreasing function. And then would we say it's increasing without bound, decreasing without bound, or increasing or decreasing toward a finite value?
It's decreasing without bound.
Decreasing without bound. So we know it's decreasing because that was our answer to part 1, right? And it's decreasing without bound because if I go further out to the right that I go, the further down my graph goes. There's no floor value down here that it never crosses. It just continues breaking through every floor down to negative infinity. Okay? So for this particular graph, we would say that it's decreasing, it's always concave down, and it's decreasing without bound. Okay? So that's how they're using the terminology here. We said what the y-intercept is. What's the range of this function?
0, positive infinity.
This? Parentheses, brackets.
Parentheses on the left side and the right side.
Parentheses on both sides. Does everyone agree with this?
No, isn't it brackets or is the 0?
Yeah.
Bracket. So
Bracket gives you-
let's talk about that piece first. What would if I put a bracket here? What would that mean?
It could equal 0.
It could equal 0.
But it won't.
What did we decide about?
You'll never hit
This
0.
it never actually hits 0, right? Because of the horizontal asymptote. It gets as arbitrarily close as how a mathematician would say it, but it never actually arrives. So I would say that the parentheses around 0 is more appropriate. What about the infinity that's happening here? First of all, why infinity?
There's no limits.
There's no limit, right? But the infinity that I wrote here is a positive infinity. Where would I find that positive infinity on this graph? Positive infinity in the range is going to be found up at the top of the y-axis. Kind of a way to think about it, right? But this graph doesn't go up there.
I was thinking about domain.
Yeah, so that's, I was noticing as I was scoring exam 1 that there's still some domain range flip-floppiness in people's thinking. So range is values of y, right? So I want to ask, what values of y does this graph actually cover? To which you notice that, oh, we cover the entirety of the negative y-axis, not including y equals 0, right? But it goes all the way down to negative infinity. So how would I revise my interval notation here to convey that information?
Isn't it just infinity, comma, infinity?
Well, so again, I'm going to ask the question, let's ask the easy question. What is the upper limit of the range? What's the greatest value that the y value can take? Right, so there's no actual maximum, but it does not go past 0 with that open parentheses, right? It gets arbitrarily close to 0. What's the least value? How far down does this range go?
Negative infinity.
Yeah, there we go. And we want the least value always to be on the left of my interval notation. So negative infinity, comma 0 would be a way to write the interval notation for the range of this. Or if we wrote it as an inequality, which comes more naturally, I think, to most people, we would write something like y is less than 0, right? So we can hit any single y value as long as that y value is negative. But if that y value is 0, or if that y value is positive, there's no corresponding t values that we can have.